Section 1 Introduction. We're going to talk about autoregressive language models, which have proven to be very effective in various language-related tasks. These models generate new tokens, or units of information, based on a given context. This process is done sequentially, one token at a time, using a method called temperature sampling. In this method, the next token is chosen from a distribution that's adjusted according to a parameter called temperature. If the temperature is 0, the model simply picks the token with the highest likelihood. This is known as greedy decoding. This token generation process can be combined with other methods like nucleus sampling and top-K sampling. However, because these methods generate tokens one by one, they can be slow, which is a problem for some applications. As a result, various techniques have been proposed to speed up this process. Before we delve deeper, let's clarify some terms. We use x(i)j to represent a sequence of tokens from the ith to the jth token. If I equals 1, we just use x(j). Xi refers to the ith token in a sequence. We use subscripts to differentiate between different sequences. For example, x_1 (t) and x_2 (t) represent two sequences of length t. We use n to represent the set of numbers from 1 to n. Now, let's talk about a simplified model of how these models work. In standard inference, given a context, the model can calculate the probability of all possible next tokens with a certain amount of computation and time. This process can be parallelized along the time axis, meaning the model can calculate the probabilities for all possible next tokens at each point in time. This process can also be parallelized along both the time and batch axes. In this case, the model can calculate the probabilities for all possible next tokens at each point in time for multiple contexts at once. This doesn't increase the computation time, which is a characteristic of the hardware typically used for neural network inference, like TPUs and GPUs. Previous methods have used a similar model to develop faster decoding algorithms. However, there may be some overhead depending on the hardware, implementation, and resource utilization. We've found that the theoretical gains are largely preserved for a large transformer model in practice. There are also efficient transformer architectures that reduce the computation cost. These approaches are separate from the focus of this paper, but they can be combined with our approach. Many previous methods have proposed guessing a few possible future tokens using an efficient model, then calculating several conditional probability distributions based on these guesses. This process takes a constant amount of time due to parallelization along the time axis. The guessed tokens are then accepted or rejected based on a statistical method, ensuring that the accepted tokens are effectively samples from the large model. This means there's no decrease in the quality of the decoded output compared to that of the large model. When the guesses are plausible under the large model, multiple tokens will be accepted, leading to a larger gain in latency improvement. We'll further characterize the acceptance probability as a function of the closeness of the distributions of the large model and the small model. While this approach has the same computation cost as standard decoding, it can significantly improve decoding latency due to parallelization. The aim of this work is to provide a thorough understanding of these approaches and discuss conditions for optimality and algorithmic improvements. We'll start by providing a more formal overview of speculative decoding and related works. Section Summary. Autoregressive language models generate tokens sequentially, but this can be slow in certain applications. To improve decoding speed, techniques like temperature sampling, nucleus sampling, and top-K sampling have been proposed. These methods allow for parallelization along the time and batch axes, resulting in faster decoding without sacrificing the quality of the output. The goal of this paper is to provide a principled understanding of these approaches and explore their optimality conditions and algorithmic improvements. Section 2 Previous works and speculative decoding. Let's delve into the previous research and the concept of speculative decoding. Earlier methods have used parallelization along the time axis to speed up the process. They first predict multiple tokens and then check if these tokens can be generated by the model using the corresponding sampling or decoding scheme. For greedy decoding, multiple tokens can be predicted by a separate model, aggressive decoding, or retrieval augmented text. For sampling, a recently proposed algorithm called speculative decoding has been introduced, and we'll explain this algorithm in the following paragraphs. Imagine we have a draft model that is computationally inexpensive and can predict the next token based on the context. The predictions of this draft model are close to those of the main model for most contexts. Let's say we have decoded for a certain number of steps and have obtained a prefix. The next iteration of the speculative algorithm can be broken down into 3 steps. 1. Draft construction. The draft model is used to efficiently and speculatively sample a certain number of tokens. We keep the conditional probabilities on the next token for each token less than the total number of tokens sampled. 2. Conditional probability computation. After observing the samples, we compute the conditional distributions in parallel, along the time axis, in constant time. 3. Draft selection. We validate and select the first few tokens given the draft sequence and the conditional probabilities from both models. We sample the next token from a residual distribution as a correction to the first rejected token. If no token is rejected, the residual will just be the conditional probability from the large model, which gives an extra decoded token. After this step, we use the next context and sample the next few tokens using speculative decoding iteratively. The key to these 3 steps is draft selection, which selects a valid sequence such that the output has the same distribution as that of the large model. In speculative decoding, this is achieved via recursively applying a token-level maximal coupling algorithm. This algorithm is applied where the conditional distribution of the draft model and the large model may be further conditioned on the newly decoded tokens. The algorithm returns a random variable which either is the accepted input or a sample from the residual distribution. The algorithm is recursively applied as long as the draft tokens are accepted to select the first few tokens from the draft model. For the first rejected token, the sample from the residual distribution is used as a correction. Previous research has shown that if the input follows the distribution of the draft model, then the output of the algorithm follows the distribution of the large model, which is exactly what we want. The closer the distributions of the draft model and the large model are, the higher the chance of the draft token being accepted, and fewer the number of serial calls to the larger model. In the ideal case, if the distributions of the draft model and the large model are the same, then the draft token is always accepted, and when used for speculative decoding we have all tokens from the draft model. Together with the extra sampled token from the large model, we obtain more tokens in one iteration. In such a case, assuming the decoding time of the draft model is negligible compared to the large model, the speedup is more than 1 times. Section summary. Previous approaches to parallelization in decoding involve predicting multiple tokens and validating if they can be generated by the model. Speculative decoding is a recently proposed algorithm that efficiently samples multiple tokens using a draft model, computes conditional probabilities in parallel, and selects valid tokens based on the conditional distributions from both the draft and large models. This algorithm aims to achieve a higher chance of accepting draft tokens, reducing the number of calls to the larger model and potentially providing a speedup of L+1 times. Section 3 are contributions. In this work, we delve into the theoretical aspects of the speculative decoding algorithm, addressing several questions. We explore its relationship with the broader field of statistical sampling, its optimality from an information theoretic perspective, and the potential for further speeding up decoding through parallelization along the batch axis. We first draw a connection between speculative decoding and the well-established theory of discrete optimal transport. This is achieved by viewing the problem of speculative decoding as a token-level coupling problem. With this perspective, it becomes evident that the selection of draft tokens is the optimal solution for optimal transport with an indicator cost function. This is also related to the problem of maximal coupling. Building on this connection to optimal transport, we demonstrate that decoding can be further accelerated by parallelizing along the batch axis using multiple drafts from the draft model. We frame the token-level draft selection problem as a discrete optimal transport problem with membership cost, referred to as OTM. While discrete optimal transport can be solved with a linear program, the number of variables grows exponentially with batch size, which can be challenging. To overcome this, we propose an efficient transport plan that approximates the optimal acceptance probability closely. With these theoretical foundations, we return to the task of speeding up decoding and introduce a new algorithm, SpecTr. We show that SpecTr can be used to derive valid sequences from the large model more quickly. The key difference between SpecTr and speculative decoding lies in the number of draft sequences sampled from the small model and the selection algorithm that chooses a valid sequence from multiple draft sequences. This requires entirely new statistical tools, and the connection between token-level draft selection and OTM is crucial for obtaining valid transport plans with good guarantees. We consider this one of the main contributions of our work. Like speculative decoding, SpecTr ensures no degradation in the quality of the decoded output compared to the large model. We demonstrate the benefits of our approach on standard datasets, showing that SpecTr achieves a speedup of 2.13x, a further 1.37x speedup over speculative decoding on standard benchmarks. We then delve into the draft selection step of SpecTr, focusing on the case when L equals 1, which is a token-level draft selection problem. Given a context, we consider a collection of draft tokens sampled from the small model. We aim to output a token whose distribution follows that of the large model, and hence is a valid sample from the large model. We also aim to maximize the probability that we accept one token from the set of drafts. When L greater than 1, a sequence of token-level draft selection algorithms could be used to select a valid sequence from the large model. The two main goals of the draft selection problem are validity and maximizing acceptance. The output token should always be a valid token from the large model, ensuring no quality degradation. The higher the probability that we accept a draft token, the more computation we can save through parallelization, leading to better speedup. These goals align with the framework of optimal transport with a properly defined cost function. We formally define optimal transport and connect it to draft selection with one draft, with the generalization to multiple drafts provided later. Section Summary. In this section, the authors address several theoretical questions regarding speculative decoding. They establish a connection between speculative decoding and the broader field of sampling and statistics, and show that speculative decoding is optimal in an information theoretic sense. They also propose a method to further improve decoding speed by parallelizing along the batch axis, and demonstrate experimentally that their approach achieves significant speedups compared to speculative decoding on standard benchmarks. The authors then focus on the token-level draft selection problem and define the main goals as ensuring validity of the output token and maximizing acceptance probability, which can be achieved through the framework of optimal transport with a properly defined cost function. Section. Coupling and optimal transport. Let's talk about coupling and optimal transport. To make things easier, let's assume that omega is a discrete domain. First, let's define what we mean by coupling. If we have two probability distributions, P and Q, we say that a joint distribution pi, which is supported over the product of the sets X and Y, is a coupling between P and Q if it satisfies two conditions. For every element Y in Y, the sum of pi, X, Y, over all X in X equals Q, Y. Similarly, for every element X in X, the sum of pi, X, Y, over all Y in Y equals P, X. We denote the set of all possible couplings between P and Q as pi, P, Q. Sometimes, we might refer to the probabilistic mapping f_pi, which is introduced by the conditional probability pi, y given x, equals pi, x, y, divided by p, x, as a coupling. This is also known as a transport plan from P to Q in this paper. We'll set P as the distribution of the draft tokens and Q as the target distribution of the output token. In this case, f_pi is a valid draft selection algorithm. We can make a claim here. For all pi in pi, P, Q, let f_pi be the probabilistic mapping defined above. If X follows the distribution P, then f_pi, X, follows the distribution Q. We'll design selection algorithms by finding valid couplings between the draft distribution and target distribution to ensure the output tokens are valid. Next, let's define optimal transport. For a cost function C that maps pairs of elements from X and Y to non-negative real numbers, the transportation cost of a coupling is defined as the expected value of C, X, Y, where X and Y follow the distribution pi. The optimal transport plan is the coupling pi and pi, P, Q, that minimizes the transportation cost. Now, let's talk about speculative decoding with one draft token. With X and Y both equal to omega, the domain of the tokens, and P and Q equal to P and Q respectively, we can define the speculative decoding objective with one draft token using the cost function of indicator cost. This cost function captures the resampling cost and is defined as C, X, Y, equals M times 1 if Y is not equal to X. The transportation cost of the coupling will be the expected value of M times 1 if Y is not equal to X. This optimal transport cost is known to be the sum over all X in omega of the minimum of P, X, and Q, X, which is achieved by the maximal coupling between P and Q. Therefore, speculative sampling achieves the optimal cost with one draft token. In the next section, we'll generalize token level selection to allow for multiple drafts. Let's say X is the set of K draft tokens from omega and Y is the set of the final sampled token from the desired distribution. To characterize the resampling cost with multiple draft tokens, we use the cost function of membership cost. This cost function is defined as C, X, Y, equals M times 1 if Y is not in the set of distinct elements in X. When K equals 1, this recovers the indicator cost mentioned earlier. The transportation cost of the coupling will be the expected value of M times 1 if Y is not in the set of distinct elements in X. We'll also refer to this cost as the rejection probability. Similarly, the acceptance probability will be 1 minus the rejection probability. From now on, we'll use membership cost as the default cost function and refer to the optimal transport solution as optimal transport with membership cost. We'll denote the coupling that minimizes this cost as pi star. The cost C, pi star, is referred to as the optimal transport cost between P and Q. We'll denote the corresponding optimal acceptance probability as alpha, P, Q, equals 1 minus C, pi star. Section summary. In this section, we define the concept of coupling, which is a joint distribution that connects two probability distributions. We also introduce the notion of optimal transport, which is a coupling that minimizes the transportation cost between two distributions. We then extend these concepts to multiple draft tokens and define the resampling cost using a membership function. The optimal transport with membership cost, OTM, is the coupling that minimizes this cost, and the corresponding acceptance probability is denoted as alpha, P, Q. Section. Draft selection with I.D. Draft tokens. In this paper, we're primarily focusing on a scenario where draft tokens are independent and identically distributed, I.D. samples from a base distribution. This approach allows us to generalize to more complex draft selection strategies, such as sampling multiple tokens without replacement or using a different distribution for each draft. We're trying to obtain a valid token from a distribution, Q, given multiple I.D. samples from another distribution, page for a specific context. We have P and Q as two different models. We set P as a product distribution whose marginals are all P, and Q as Q. The optimal transport problem we want to solve is to minimize a cost function subject to certain constraints. We denote the optimal acceptance probability as alpha underscore K, P, Q, which is a measure of how likely we are to accept a token. We've found that this probability has a few interesting properties. For instance, it's monotonic, meaning that for any P, Q, and K, the number of drafts, alpha underscore K, P, Q, is less than or equal to alpha underscore K plus 1, P, Q. Also, if the ratio of Q, X, to P, X, is bounded for all X, then as K approaches infinity, alpha underscore K, P, Q, approaches 1. Otherwise, it equals the sum of Q, X, for all X where P, X, is greater than 0. These properties show that as we increase the number of drafts, K, the value of alpha underscore K can become large, which means that the acceptance probability increases, leading to faster computations. We then focus on computing the optimal transport plan and the optimal acceptance probability. This problem has been extensively studied in the field of discrete optimal transport, and it can be formulated as a linear programming problem. This problem involves minimizing a sum subject to certain constraints. The linear program has a large number of variables and constraints, but it can be solved in a time that is polynomial in the number of variables and constraints. We refer to the optimal coupling obtained as OTM-K. For the case of K equals 1, there is a simple expression for the optimal acceptance cost, but for larger values of K, we don't know of a general simple expression. However, we provide an upper and lower bound, which is close to the actual value up to a constant factor. We also note that while solving the optimal transport problem gives us the plan with the highest acceptance probability, using a generic linear program solver can be computationally expensive, especially when the vocabulary size or the number of draft tokens is large. In the next section, we will present a selection algorithm that can be computed efficiently and show that for any pair of distributions, the acceptance probability is at least a certain value, where the upper bound is defined earlier. Section Summary. In this section, the authors discuss the problem of draft selection when the draft tokens are independent and identically distributed, i.d. samples from a base distribution. They introduce the optimal transport, OT, problem and define the optimal acceptance probability as the solution to this problem. They also provide properties of the optimal acceptance probability, demonstrate the computational complexity of solving the OT problem, and present an information-theoretic upper bound for the acceptance probability. Finally, they mention the limitations of using generic linear program solvers and introduce a more efficient selection algorithm. Section 6. Draft selection via K-sequential selection. In this section, we introduce a sequential selection algorithm, referred to as K-seq, which provides an approximate solution to the optimal transport problem. This solution is still valid as it meets the constraints of the problem, but it's not the exact minimizer of the cost. The algorithm can be computed efficiently, taking almost linear time in relation to the size of the set omega and logarithmic time in relation to k. The algorithm works by sequentially going through all k samples generated from a distribution P, and deciding whether to accept each sample based on the ratio of Q, x_I, to P, x_I. The algorithm will output the first accepted sample, or if none of the samples are accepted, it will output a result from a residual distribution. To ensure that the probability of accepting a sample from the set omega is at most Q, x, we select an appropriate value for rho within the range of 1 to k. We then accept a sample with a probability that is the minimum of either 1 or the ratio of Q, x_I, to rho times P, x_I. This is a modification from the single draft case where the acceptance probability was the minimum of either 1 or the ratio of Q, x_I, to P, x_I. We demonstrate that a family of joint distributions induced by this method are indeed valid transportation plans from P to the power of k to Q. To find the best transportation plan within this family, we only need to search over a single parameter, rho, which significantly reduces the computation cost. We also show that searching over this subfamily of couplings won't decrease the optimal acceptance probability by a constant factor. We present a theorem that defines a function beta_p, q, rho, and a solution rho *** to a specific identity. When rho is greater than or equal to rho ***, the coupling in the algorithm is a valid transport plan from P to the power of k to Q. When rho equals rho ***, we have a performance guarantee that the acceptance probability is at least 1 to 1 e times the upper bound of the acceptance probability in the optimal transport problem. The solution rho ** can be computed efficiently using binary search over the set 1, k. We provide examples of distributions and plot the acceptance probability of K-seq and compare it with the optimal acceptance probability. We find that K-seq could have a worse acceptance probability compared to the optimal transport solution for certain cases, but there are also cases where K-seq achieves the optimal acceptance probability. We also compare the acceptance probabilities for our proposed token-level selection algorithms using a few simple examples. For instance, we consider pairs of Bernoulli distributions, which are distributions with a probability b of getting ahead. We plot the acceptance probability comparison between the optimal transport method and K-seq for different Bernoulli distributions as a function of k. We find that when the distributions are equal, the acceptance probability is always 1 for both methods. When the distributions are not equal, the acceptance probabilities for both methods increase as k increases before they reach 1. In some cases, K-seq has a worse acceptance probability compared to the optimal transport method, but in other cases, the two algorithms have the same performance. Section Summary. In this section, the authors propose a sequential selection algorithm called K-seq, which provides an approximate solution to the optimal transport problem. The algorithm efficiently computes the solution by sequentially accepting or rejecting samples based on the ratio of the target distribution to the reference distribution. The authors show that the algorithm produces valid transportation plans and can be computed with reduced computational cost. They also compare the acceptance probabilities of K-seq with the optimal transport map solution for different distributions and demonstrate cases where K-seq achieves optimal performance. Section: Pairs of uniform distributions. Let's talk about pairs of uniform distributions. Imagine a uniform distribution over a range, which we'll call U, D. We've plotted the optimal acceptance probability for different uniform functions Q, based on a variable K. For these distributions, it's been shown that a sequence of K-seq, achieves the optimal acceptance probability, which we'll call alpha_K. We've only plotted alpha_K, because it's the only one that matters in this context. What's interesting is that all acceptance probabilities increase in a consistent manner and approach 1 as K approaches infinity. Now, let's move on to the application of optimal transport maps, OTM, in autoregressive sampling, which we call SpecTr sampling. This process is similar to speculative decoding and can be broken down into 3 stages. 1. Draft set construction. Given a current context, x_t, we use a draft model to sample a set of draft sequences of length L, which we'll denote as S. We keep the conditional probabilities for all possible outcomes. 2. Conditional probability computation. We calculate the conditional probabilities for the next token for the large model in parallel. 3. Draft selection. We select the first L_prime of the L tokens and set x, t plus I, equal to z, I, for I less than or equal to L_prime, and some z in S. We then sample a token from a residual distribution as a correction to the rejected tokens. The computation of conditional probabilities takes constant time when the size of S is not large, based on our simplified computations model. In this section, we mainly focus on the draft set construction phase and draft selection phase. To construct a draft set, given a context x_t, a straightforward way is to independently sample K draft sequences from the conditional distribution. However, this method can be generalized to a prefix tree-based algorithm, although this generalized version didn't perform better in our experiments. For draft selection, we present a sequence-level selection algorithm given a set of draft sequences. The algorithm works in a recursive manner. Given a prompt and a candidate set S, the algorithm first computes a token-level draft selection algorithm, which is a transport plan. This plan is then applied to the set of first tokens of the draft sequences in S to obtain a valid token. If this token is not the last one, we filter out sequences in S whose first token is not the selected one and denote the remaining sequences as S_next. This process continues until we have only one token left or S_next is empty. If the selected token is the last one and it's in S, we have the option to sample an additional token since its conditional probability is already computed in the second phase. Due to the properties of the token-level selection algorithms and the autoregressive structure of language models, it can be shown that the selected token is always a valid sample. Let L_prime be the number of decoded tokens in one iteration. This is a random variable in the range 1, L plus 1. The quality guarantee of the decoded tokens is stated in a theorem, which we prove in the paper. The theorem states that if all drafts in the set S are generated from the small model with input x_t, then the output satisfies that the newly decoded tokens are distributed according to the large model. Section summary. In this section, the authors discuss the use of optimal transport mapping, OTM, to accelerate autoregressive sampling, which they refer to as SpecTr sampling. They describe the 3 phases of SpecTr sampling: draft set construction, conditional probability computation, and draft selection. They also present a token-level draft selection algorithm and provide a quality guarantee for the decoded tokens. Section 8 Experiments. In this section, we'll discuss the experiments we conducted to evaluate our method, SpecTr, and compare it with 2 other methods. 1. The standard autoregressive decoding, and 2. Speculative decoding with K set to 1. It's important to note that all 3 methods generate samples from the same large model, so the quality of the speculative decoding methods is not influenced by the large model. Therefore, our focus will be on measuring the increase in speed in our experiments. We made a couple of assumptions in our simplified computation model. 1. the time it takes to decode from smaller models is insignificant compared to decoding from the large model. 2. Running tasks in parallel along the batch and time axis doesn't increase the time for a single call to the large model. With these assumptions, the theoretical speed increase compared to standard decoding will be the average number of decoded tokens per single call, a concept we refer to as block efficiency. However, when we actually implement the SpecTr algorithm, the real-world speed increase is affected by several factors. These include: 1. The decoding time for the smaller model might not be insignificant. 2. Running tasks in parallel might increase the time for a single call to the large model. 3. Additional functionalities in SpecTr, like the draft selection algorithm and switching between models, might introduce overhead. These factors will vary depending on how the algorithm is implemented and optimized. In our experiment, we considered both the block efficiency and the average real-world speed increase with our implementation of SpecTr. We first evaluated the performance of our algorithm and compared it to speculative decoding using state-of-the-art PaLM-2 models with prompts from the 1 billion language benchmark, LM1B. We used a pair of smaller transformer models to analyze the different factors mentioned above. We used PaLM-2 Gecko and PaLM-2 Bison as the small and large models, respectively. The real-world speed increase was normalized by the latency of the standard autoregressive decoding. The time we logged included all the factors mentioned above. In the configurations we considered, the real-world speed increase grew as K and L increased. As shown in the table, the actual real-world speed increase was less than the theoretical speed increase of block efficiency, which is what we expected. However, the benefits from SpecTr outweighed these overheads. Specifically, when L was set to 8 and K was set to 8, our proposed SpecTr algorithm had a speed increase of 2.13 times, a further 1.37 times increase compared to speculative decoding, K set to 1. We would like to express our gratitude to Asaf Aharoni, Kwangjun An, Bada Ghazi, Sanjeev Kumar, Teodor Marinov, Michael Riley, and NeurIPS reviewers for their valuable comments and discussions.